Hello everybody, welcome to our final presentation. Our project name is the Clapper 2.Awesome, and today we'll be going over all aspects of our final capstone project. My name is Mark Hemmings.
And my name is Joshua Esquadro.
On the next slide, we'll be going over the agenda, which covers all major topics of our presentation.
So for our agenda, below is the list of the major topics we will go over in today's presentation. For our project purpose, the Clapper 2.Awesome is a clap-activated system that will toggle power controls of any connected 120-volt AC devices, while also delivering wireless control features. Previous iterations of Clapper devices have become outdated and have failed to keep up with modern industry standards. So overall, our team plans to modernize the Clapper by adding new features such as an improved filter, wireless connectivity, sensitivity adjustment, and LED status lights display.
Moving on to the planning documents of our capstone project, the first being the Gantt chart. So after making this portion of the project, we really didn't use it too much, mainly because after the first week or so, the start and finish dates that we had set at the beginning of the semester became extremely inaccurate, so it was hard to use this with much success. Moving on to the WBS though, other than the estimated hours for each task, we really use this mainly throughout the entire project to organize our time and stay focused on certain tasks. We worked through it from sections 1.0 to section 4.0 in chronological order, and as I stated previously, it was key to staying on track and helping us organize our work.
For our project scope, here are our deliverables. The device will only detect the clap audio frequency, which is sensed through the electret microphone. And for what it controls, the device will act as an electrical switch to power on and off any 120-volt AC devices connected to it.
Moving on to the new features of the Clapper 2.Awesome, all of the items are listed below. First being improved bandpass filter. Next, sensitivity control using a potentiometer. Power status LEDs, both red and green. Wireless on and off controls. And lastly, powered from a wall outlet, which we'll get into a little bit later.
This is our first DC concept circuit. It includes most of our main components in our final build, and we designed the schematic using the Multisim software. Moving on to the next slide, here's our final DC circuit schematic to represent the connections on our final build. On the left, you can see our sensor, the electret microphone, the RC bandpass filter, the op-amp, and the R6, which is the potentiometer, which is configured as a feedback resistor for sensitivity adjustment. The analog signal goes to the voltage divider, which is then converted to the ADC chip and sends a signal to the Raspberry Pi.
Moving on to the DC measurements. We had previously discussed this in other presentations, but we'll go over it again. In the tables on the left, we recorded voltages from the microphone, green being from the microphone itself, and dark blue being after the filter itself. Moving on to the filter, we have an RC bandpass frequency response graph, which shows how the filter reacts between a certain frequency range, being 1000 Hz to 4000 Hz. In the bottom left, we have a pink table, which we used as a calculator. So we input the input signal we wanted in the output signal, and it helped us find the desired gain. Then moving, lastly, to the light blue tables, we worked with different desired output signals as well as different gains. We worked with a few different combinations, and on the bottom table, we felt that these specifications fit our project needs the best. Moving on to the AC schematic, this is the first revision of the AC schematic, and overall it's quite complete and it accurately represents the final, but we definitely felt there was more we could do to clean it up and make it more professional. Moving on to the final AC schematic though, we labeled off certain portions of the AC schematic and also rewired certain parts that are connected to the Raspberry Pi's GPIO pins. We had made some changes when we soldered components onto the PCB due to limited room, so those changes were necessary on the final schematic.
And in this slide, here's our functional code to control the relay module and the LED power status lights. In this code, we imported all the necessary libraries, configured the ADC chip and its GPIO pins. We declared our global variables and set initial conditions for starting the program. And lastly, on the right, we have an infinite while loop that reads voltage signals, comparing it to a set threshold and determines, based on that result, whether to deactivate or activate the relay.
Moving on to the construction of the project. This picture represents the final build of our project, which we have today. You can see on the left the Raspberry Pi 4, which is connected to our PCB with all final components and systems soldered on. You can see the wiring connected to the relay module, and you can also see the PVC enclosure for the AC side of the project. In the next slide, we'll talk about, in a video, the demonstration of the actual construction.
Here's the video of the construction of the Clapper 2.Awesome.
So now we'll go over the construction of the final build for our Clapper 2.Awesome. We'll start with the AC section of the circuit. So this is the enclosure for all of our AC components. It's finger tight and it's covered in PVC. It's a PVC box to protect against everyday use. On the front end, we have a circuit breaker status light, which will be on when the circuit is live. We have the connections to our main switching component, which is the relay module, and that is connected to our DC circuit. This is the AC in cable, and this is the AC output, which we have connected a lamp as our output for this demonstration. If you come with me to the right, we have our AC input connected to an extension cable. When I plug this into the wall, you will see that the circuit breaker status light is now on, like I said before, indicating that the circuit is live. Moving over quickly to the DC circuit, we have all of our components soldered onto the PCB, everything listed in our deliverables. Our circuit is being powered with 5 volts from our Raspberry Pi 4, and the main powering for the entire circuit comes from this USB-C connected to the wall. So that concludes the construction of our Clapper 2.Awesome. So
Next slide.
Now we will demonstrate how to power on the Clapper 2.Awesome.
Here's just a quick demonstration of the functionality of the Clapper 2.Awesome. So the code is now running. As you can see, the LED status light is turned to green, which shows that the power is on and the output lamp is also turned on.
Here's a video of powering off the Clapper 2.Awesome.
Here's a quick demonstration of me turning off the Clapper 2.Awesome.
Next slide.
Now we will demonstrate how the bandpass filter functions in the Clapper 2.Awesome. Now we'll demonstrate the functionality of our sound filter. So first I'll start with snapping into the microphone. Now I'll demonstrate with, say, setting a coffee cup down a little loud. And for the last demonstration we've been doing the entire time, we've been talking and it's never activated the microphone through voice. So as you can see, we are running the program on the Raspberry Pi, so there's no rigging of this demonstration. And lastly, I'll clap to just prove that the filter works. Now
And here's the video or the sensitivity adjustment at its max gain.
This is our sensitivity adjustment at max gain. This is our
Next slide.
Now we will demonstrate the sensitivity adjustment at its lowest gain.
So now I will demonstrate the sensitivity adjustment to its lowest gain. See, it's turned all the way. And as you can see in the code is running. And then I will demonstrate to you guys that the circuit will now be unresponsive from my claps.
Here's the video for the wireless control feature of the Clapper 2.Awesome.
I'll quickly demonstrate the wireless control feature that we have in our Clapper 2.Awesome. As you can see in my app, we'll be using the RASP controller, which is available in the App Store and which is also free. If I press this button, it will power on the circuit and will turn on the lamp. As you can see, the power is on and the lamp is also on. And if I press it again, which we will turn off the lamp. So 0 will indicate off and 1 will indicate power on.
Next slide.
Now we will talk about the timeline and budget portion of our project. So when looking at the WBS's planned hours versus actual, we found that the planned hours was recorded to be 168 total hours, whereas with the actual hours, we only put in 121.5 hours total. So we definitely performed the task quicker than we had expected. Some of the things that held back our timeline and budget though, so we had poor initial WBS and Gantt structure, as kind of previously mentioned at the beginning of the presentation. So with this, mostly the Gantt, but also the WBS at times became not easy to follow and not worthwhile and was hard to follow. When looking at inconcise component selection, we knew what systems we wanted in the Clapper 2.Awesome, along with the new features, but we didn't spend as much time as we should have looking at the specific components for these systems. And it caused our budget to kind of rack up in price and also have higher quantities of items than we would have desired. For sporadic project pacing, though, we would go a few days without working on the project much, but then spend 1 to 2 days, multiple hours within those days, working on the project hard. So when looking at the fact that we have under the estimated hours total, we should have finished this project weeks before the end of the semester, but in reality, we finished close to the end of the semester and didn't have as much time as we had wished or could have to improve the project even more.
And in this slide, here's our final timesheets throughout the course of the project. This represents the actual work hours we put in the project, and it's a breakdown on the amount of hours and the dates we completed our task. And at the bottom of each of the tables, we each have our total hours to show our contribution to completing the project.
When looking at the final budget, we spent a total of $454.75. Like I had mentioned previously, some of the quantities on this list are higher than they should have been due to inconcise component selection. But overall, all the items on this list are at least used once throughout the project, either in an earlier version of the Clapper 2.Awesome or the final build of the Clapper 2.Awesome. Moving on to project issues, there was a few key issues that we felt were good teaching moments throughout the entirety of the project, or lessons learned, as you could say. The first one being the removal of the 9-volt battery. We had initially planned on powering the entire DC side of the circuit with a 9-volt battery, but upon going further into the construction of the circuit, especially once we were controlling a relay module with the Raspberry Pi 4, we realized that powering the circuit through the Raspberry Pi was a better option. Next was the Salem key. We spent time purchasing, building, and testing for components on the Salem key, but then realized our research was insufficient and that the Salem key was not the right fit for our project at all. The RC bandpass ended up being the correct solution in the beginning. Electric microphone replacements. We had initially bought some cheaper electric microphones, and this caused inconsistent results for audio pickup and voltage signals. But once we purchased better electric microphones, we were getting more consistent results. Next, improper test circuit wiring. We had a lot of looping wires and protruding objects on our breadboard, and this caused issues when we were transporting it, say, from home to the lab or from house to house, where the circuit would not work as well or just not work in general. So once we cleaned up the breadboard near the end of the project, we noticed that our circuitry that we did have worked way more consistently. And lastly, ADC voltage divider solution. With this, we were having a hard time reading voltage at the ADC pin consistently or even at all at times. But once we did a little bit of research and discovered we could set up a voltage divider at the pin, we were getting way more consistent results, and we're actually able to move on to the software portion of our project.
And overall, the project was a success. We have completed all the tasks on time following the WBS. There are some things that could have been changed or added for the device to function perfectly. If we had better plan in the beginning, we could have made the device work consistent and refined. The project itself allowed us to incorporate all the knowledge we have learned throughout the course of our program, and we have also expanded our knowledge in regards to designing circuitries and applied our troubleshooting skills. The biggest takeaway from this experience is the initial planning and timeline of the project, as these are the critical aspects of successfully completing the project on time. And now we are open for questions. Thank you so much for listening to our presentation, and thank you for taking the time to be here.